Hello everyone and welcome to the channel. In this video we'll start the routing of the 65816 breakout board PCB I've been working on for the past few episodes. If you haven't watched the previous episodes already, I recommend you start with part 1 where I explain what I'm doing and then come back to this episode. I hope you enjoy! Alright, so let's get started with the routing. Off camera, I went ahead and did some cleanup on the KiCad schematic. You'll see that I removed the hierarchical sheets and was able to fit everything in a single A3 sheet, which I think is a bit better. This way you can have everything in a single view and it's a bit cleaner. Before we start the routing, we need to assign footprints to all our components. So when assigning footprints, I like to divide my windows because as you can see when you click on a component, it pops up in the schematic view. So it's useful to have both of them side by side. And the other thing that's useful is to click on a random footprint here and say view selected footprint. This way when you click on footprints, it will show up on the left here and you can see what you're doing. So let's get started. For my 220 microfarads capacitor, we're going to look into the capacitor library. It's a radial polarized capacitor and we have to measure the pitch and the diameter of the part. And for my part, I'm measuring a 6.5 approximately diameter and a 2.5 pitch. We're going to select this one. It has a 6.3 diameter and a 2.5 pitch, which is correct. My second polarized capacitor is a bit smaller. It only has around 4 diameter and I think it's the same pitch. Actually, it might even be smaller than that. It's 1.5, so you can select 4 and 1.5 here. My decoupling capacitors are not polarized, so it's a disc capacitor and we have to measure the width and depth and the pitch. The width is around 2, the depth is 3.4 and the pitch is 2.5. So we'll select the 3.4 with around 2 of width and 2.5 of pitch. There we go, and so we can assign it to all of these. Okay, my power LED is a green 3mm LED. We'll find a 3mm LED here. The diode has a 2.7 diameter, which is DO41. And we'll put it horizontal with a pitch of 7.62. So it's more compact. And I just want to check the size of the leg here because on my part it's quite big. It's almost 1mm. So let me measure this here. And yeah, this will work. Okay, for the connectors, I'm gonna use pin headers with a 2.54 pitch. And we need 1 times 16. So that's the one. 1 times 40. That's the one, and 18. That's the one. Now for the resistors. My resistor has a length of 6.3mm and a diameter of 2.45. So that's the size that we need. And we'll make the pitch as small as possible. So that's the one. And we can apply it to all of them except the jumpers and the resistor networks. Okay, for the jumpers, I'll talk about it in a minute. Let's do the resistor networks. This is an R array, single inline package with 9 pins, because there's 8 resistors plus a common pin. And we can apply that to all our networks. Now, the switch. So my switch is a square with a size of 6mm. So that should be the one. And then for the ACs, we can use package dip, and they are all 14 pins, except the 112. And I think the buffer and the latch. If we check the power supplies, power pin is on the 14th pin, except the IC 112 and the DS1035. And then the buffer and the latch are both 20 pins. So this one is 16. This one is 40, that's the CPU. And the DS1813 is a TO package, TO92. It has inline pins, so we have to use TO92 inline. And I'm just going to verify the pinout, and that's correct. So this is the right one. So these are 20 pin dips, and the DS1035 is 8 pin. All right, and finally the oscillator. We'll use DIP8. There we go. Now we have to talk about the optional 0 ohm resistors. So I don't actually want to solder 0 ohm resistor to the board. And so if we look at the jumper footprints, it's all solder jumpers, but they don't have the possibility to solder a resistor. And I don't think there's anything else in the KiCad's library for this use case. So I will take a resistor footprint, the same that we are using for all the resistors. And I'm going to create a copy of it. And I will just simply add a track connecting the two pads. And I'm making it a bit wider. Okay, now you can see by default it's connected. You don't have to solder anything. But if you want, you can cut the trace and add a resistor in its place. And I will add something to the cell screen so we know it's not just a simple resistor footprint. There we go. I guess that works. All right, so let's use this new footprint for all our optional resistors. Okay. Now for the DC jack, this is the one I purchased. Unfortunately, there's already no stock anymore, but I guess it's a standard format, so I'll be able to find alternatives. But what's interesting about this one is that the distributor provides the symbol, footprint, and 3D model. So if you click on that, you can see that we have a 3D model of the jack that's going to be useful later. We have a footprint and a symbol. Unfortunately, if we click on download ECAD models, it's going to require a software that's called the library loader to load this into KiCad. I don't really want that, but you can copy the reference and go to componentsearchengine.com. And if you get this reference, you'll find the exact same data that Mauser has on the website. You have the same 3D model, and you can download this. And what you'll get is a zip file that contains the data for all the CAD softwares. So we're going to go to KiCad and we're going to open the footprint. So we're going to open the footprint editor, go to import footprint. Now we also want to keep the 3D view. So I'm going to go to 3D and copy the step file into our footprint library. Now if we go to the footprint properties in the 3D models, we can see that it can't find the 3D file. And we have to update this path to point to the location within the project that it exists. And now we can find it. And we have to verify that everything is aligned, and that's right. Okay, that's good. Let's save this and go back to our footprint selector. And we have to reopen this window. And now we can see our DC jack. Now there is one issue, and that's the built-in symbol for the DC jack uses numerical pins, and this uses A, C, and B. So I'm going to edit this footprint again. So on my part, this pin here is connected to the center pin, and that's pin 1 on KiCad symbol. And this pin here is connected to the barrel, so that's pin 2. And then this pin is the switch. And so we actually have to update our symbol here to account for that. So we're not going to use this one, but barrel jack with a switch. And this has the right number. So 2 is the barrel, 1 is the pin, and 3 is the switch. And this was J1, and we're not going to use the switch, so I'll put a no connect here. But we have to update the footprint to match, and so C is actually 3. There we go. Okay, so I think we have assigned all our footprints. Let's move on to the PCB editor. Okay, so I've been trying a few designs off camera just to get a feel for the components and how they fit together. This first one was an attempt at making everything fit into a 100mm by 100mm board. It kind of fit, but it was very tight, and I couldn't see a solution for hooking up to the breadboard with all the signals that we needed. So I decided to scrap it. I'll probably go back to this format later when we have CPLDs taking off all those ICs from the board. This is a second test I did, trying to see how I could hook up the address bus and the data bus with the buffer and the latch and all the pull up and pull downs. It kind of works like this, but it makes the board very tall, and so I'd rather have the CPU rotated 90 degrees. This is another setup that I'm working with at the moment, with the CPU the wrong way around. It kind of makes it possible to route everything in a quite compact way, but I haven't put any of the pull up and pull downs. One thing I'm noticing is that the data bus and the bank address all come from the multiplexed bus here, and it would make sense to have them together. And so I think I'm going to put the data bus on the left here next to the bank address. So let me do that now. So it's just a matter of switching out these two buses. There we go. And I'm going to retry this. Okay, so this is starting to take a bit of a better shape. I have the address bus and the data bus fully routed in this example. There are two inversions with orientation, inversion with vias that need to happen here and here, because the CPU doesn't have the pins in the right order, but otherwise it looks good. I'm going to need to add an exclusion zone here to leave space for the seal screen to show the legend of the output pins. And here is the multiplexed data and bank address bus, and I think we might be getting a bit too long here. I'll start again, still only trying to experiment and see what works in terms of the routing here. I've tightened up my placements. And just for reference, so I've hidden the fabrication layers, but this is the bank address latch, this is the data bus buffer, and this is the CPU. And this is the first OR gate that helps us determine the bank 0 signal. So I've added my exclusion zone here so that we make sure that we don't put vias or pads or components where there is seal screen. And I've added a legend for all the output pins here. Okay, so let me start routing this again, and I will start by the easy stuff. So the resistor networks are placed so that these connections are quite easy. And I need to change my grid, so I usually route on a 10 mil grid. This way I can get reasonable symmetry between tracks. Let's do data bus. So if there is an angle that you don't like, you can just redo it and KiCad will delete the old track. And I'm using the shove mode of the interactive router, which pushes tracks and vias around when you add new tracks. So over here, I want to leave space for these signals to come in. So I'm gonna take this and drag and push this to the top. There we go. Now let's do the bank address. So that's the bank address. Now let's look at this section. As you can see, there's an intersection that's not great. That's because the pins on the CPU are reversed compared to the pins on the output. So I will use a via to invert them. And I usually like to come back and drag things around so that it looks nice. Alright, I don't think I'm gonna manage to get it much better than this, but I think it's pretty good. Now let's look at A12 here. And I guess we'll change sides for these. So the same thing is happening here. We need to invert the order of the data and bank address bus. So I'm progressing with the routing, but I'm already noticing an issue. This is basically where the CPU control signals are going to live, and they all need to go all the way over here. So they need to go around the buffer and the latch and come down here or go through this way. And it's probably going to work, but if you look at the reset, for example, which is here, it will have to come all the way like this. The clock, which is another important signal, is going to have to come all the way over here. I need to think more about this. Right, so I think this is much better now. The CPU is closer to the control lines. The data bus is driven with very short traces here. The multiplex data and bank address bus is a bit shorter, and the bank address is a bit longer, but I think that's fine. So I think I will keep this. I'm going to start routing other areas. I'll start by the power. So we have the two capacitors here, and then the power LED. Where's its resistor? So the power first goes through the big decoupling capacitor and then through the small one, and then it can power devices. After that, we'll have the clock section. I think there's an issue here because the pinout is not the right one, and I think that's because, yeah, I used dip 14 here. So let me change that. We want a dip 8 oscillator. There we go, and then we can update the PCB. And yeah, now we have the correct values. So first it needs power. There we go, and I need to add the decoupling capacitors, so let me just grab two. That's actually not the right one, that's for the resets. And so for every gate, I'm going to make sure that the power first goes to the capacitor and then to the chip. And actually, because this is also the resets, I will move it here. And then I can place the reset capacitor here and the button as well. Let's see what it looks like in the 3D viewer. Looks good for now. So this is bank 0. I'll do that later. Let me first work on the resets. So here is the 8 MHz signal. I would like this on the top flip-flop, so I have to invert it between 15 and 11. Okay, so 15B. I switch with 11B. Let's update the PCB. Okay, then I can take it directly from here. So now we have here the output reset signals, and I'm going to route them to the output connector. There we go, and we also have to send this all the way to the CPU. Now let's not forget the DS1813. I'm not a huge fan of this routing here. So let me try to move things around here a bit, see if I can get a better routing. Yeah, I think that's much better. And we can also route it to the output connector. And I'm going to invert the order of these. We want MR and then not reset. There we go. Now this should be easier to route. There we go. And of course, we have to remember to update the labels. I think it'll be easier if I switch around some of the reset flip-flops. I kind of started routing without setting up my board, and I need to set up the inner ground layers, so let's do that now. So we're gonna do 4 layers, and the 2 inner layers are going to be ground planes. So let's draw the ground plane. On both inner layer, it's going to be ground. There we go. So in the default settings, we can see that the ground plane doesn't go around the pads, and that's not good because if we have signals that are like here crossing here, there's a hole in the ground plane, and so that's not going to be good for signal integrity. So we have to edit our filled zone, and reduce the clearance. And there we go. And now we have a nice ground plane on the whole board. Alright, so this section is coming along nicely. Now let's do the DS1035 and the clock phases. So we do need the buffer. It would be nice to switch the clock enable pin and the clock source pin on the output connector. So we have made good progress on the reset, clock and power section. Most of the signals are now routed and they're ready to go to drive other devices. And I think we should have enough space to do that here. We might even be able to make the board a little bit smaller, maybe. We'll see. This is what it currently looks on the 3D viewer. And yeah, I'll pick this up tomorrow. All right, let's start again. So I'm going to start by the clock termination here. So there's some weirdness with my footprints for the 0 ohm resistor. I think this is a track, and so I think it's conflicting with the routing I want to do. Would be nice to invert pin 9 and 10 on this OR gate, as they are currently crossing in the PCB. Similarly, it might be nice to switch the two bottom OR gates in U8 to facilitate the routing, and to uncross the input pins. And same thing on the other gate. And here's all. Swapping the buffers around will also make the routing easier. As well, swapping the resistors in the resistor network. So this is the final clock signal. I was able to route it in a continuous shape, not in a star shape, which is better. However, that makes it quite long, and we're probably gonna have to make use of that termination resistor. I've also finished adding all of the ICs, and so now it's just finishing to route all the signals and making progress one signal at a time, I guess. Let's get back to it. Another batch of good progress. I've added the pull up and down resistors here and kept routing over here. And one thing I'm doing as well is every time I use a via to go to the other layer, I add a ground via, and this is to maintain signal integrity. Now the remaining signals are going to be a bit more complicated, but we'll see how it goes. So a bunch of things are remaining. First, let's look at the 3D viewer, see if the placement makes sense. I think it does. So we have a bunch of wasted space here. The resistor network placement here is not ideal. We could make this shorter on the right here. We have a bunch of space here as well, and here on the left. But otherwise, it's pretty nice, pretty compact. On the front and back, I'm going to add VCC fills, and that's going to help me with routing the power. Alright, so there's a few signals left, but I'm not going to spend too much time on these. I think this placement is going to work. What I'll do is I'll take a screenshot of this and remove all the tracks, and then I'll do it again. And I'll try to make the component placement a bit tighter and nicer, and then I'll redo the tracks for the final version. And that's going to be the subject of next week's video. So this video was getting quite long already, so I decided to split it into 2 parts. Next week we'll cover the improvements I made to the component placement, to the board setup as well, because I didn't really do a good job of setting up my design rules in this first draft attempt, and we'll finalize the board and send it over to the manufacturer. So stay tuned for the next video. In the meantime, if you have any questions or feedback about this video, please let me know in the comments, and I hope to see you in the next one. Goodbye.